the previous video, we used a simulation to compare means for an unrestricted sleep group and a sleep-deprived group. We're going to come back to that same example in this video, except this time we're going to do a theory-based test. So for a theory-based test, we want to start off by calculating a standardized statistic. So this is a familiar formula, the statistic minus the null hypothesis value divided by the standard error of the statistic. So we have a quantitative response here, so this is going to be a t-statistic. And the regular statistic that we used to summarize in our simulation-based test was a difference of means. So this whole thing, x bar for one group minus x bar for the other group, that whole thing is the statistic. The null hypothesis value is going to be 0 because our null hypothesis is that there was no difference between the groups. And then we have a new formula for the standard error. So this looks a little bit like what we saw for one mean. We have the standard deviation squared divided by n, that's for one group, plus the standard deviation for the other group squared divided by n. Side note, and you don't have to write this down, but it looks a little bit more familiar if you notice that this is the same thing as this. So our textbook usually writes it with s over the square root of n when it's talking about one mean, and then it writes it the other way when we're talking about two means. But you don't really have to worry about that as long as you know that that's the standard error for the difference of means. So this number here is the standard error of x bar 1 minus x bar 2. All right, so let's plug this in. We've got 19.82 minus 3.90, that was our statistic, minus 0 for the null hypothesis value. And then I'm just going to plug in the standard deviations for the groups, 12.17 squared, and the sample size for that one was 11, plus 14.73 squared, and the sample size for that one was 10. So we can plug that into Desmos or some other calculator, and I got 2.685. And what's nice about using a t-statistic is that we can model what would happen if the null hypothesis is true using a theoretical distribution. So this t-statistic that we just calculated has approximately a t-distribution. The degrees of freedom here, though, are kind of a nightmare. To get the degrees of freedom, you would have to use this formula, and it's as hard to say it as it is to calculate Satterthwaite approximation, something like that. So we're going to skip all of that and just let technology do this for us. We might as well just let the computer do the whole thing. There's really no reason to even plug into the standardized statistic. There's a great chance you'll make a mistake, and it's more efficient just to let the computer do it for us. So I'm going to do the theory-based inference applet. And there's actually two different ways that we can do this. We're going to go down to two means. And one way would just be to type in the sample sizes, the means, and the standard deviations for each group. The other way is to actually paste in our data. So I'm going to copy the data from this applet, and the format of that was stacked. So by stacked, they mean that you've got like the group on the left side and then the response on the right. Also, it had headers in it. So I'm going to clear this out and paste in my data and click Use Data. And I can tell that it worked because I've got my plot, I've got my statistics, and I've also got the difference in means here. And when I click Test of Significance, it's doing unrestricted minus sleep deprived. I want to do the greater than test, so I change it to greater and then click Calculate. And it does everything here for me. My t-statistic 2.69, that's the same as we got by hand. It gives us the degrees of freedom. We avoided that horrible formula, 17.56 degrees of freedom, and it also gives us the p-value. So we find our t-statistic, 2.685, and then we're comparing this to a t-distribution with degrees of freedom 17.56. So remember, there's different versions of the t-distribution depending on how big your sample sizes are. So the details behind the scenes are a little bit complicated, but we're using it the same way we've used a theory-based distribution in the past. So to calculate the p-value, we're going to shade all of the area under the curve to the right of our statistic. And the reason that we're doing it to the right of our t-statistic is because this particular test, we're looking at a greater than sign in the alternative. So So it's always going to be more extreme than your t-statistic. And when we did that here, our p-value came out to be 0.0077. So very similar to what we got from the simulation. This is still giving us very strong evidence that there's a difference between these two groups, right? That the sleep deprivation did have an effect. To calculate our interval, again, we're doing a difference in means as our statistic. Our multiplier here is going to come from the t-distribution, so this is going to be a t-star, but again, it's going to be difficult to do that ourselves because the degrees of freedom are so complicated. So we're going to let the computer do this whole thing for us. But then the standard error would be that same formula we saw before, the standard deviation for group 1 squared over the sample size for group 1, plus the standard deviation for group 2 squared over the sample size for group 2, and that's all under the square root. So it's super easy. In the theory-based inference applet, we just click confidence interval, and we get our values here. So we think the difference of means is somewhere between 3.4413 and 28.3987. So that's a little bit different from what we got from the simulation-based approach. That's because the standard deviation there was coming from a simulation, so it's not exactly the same as what you get when you calculate using the formula. Still a really wide interval though, because our sample sizes are so small, we don't have a very precise estimate here. So just like any theory-based test, we need to check the validity conditions before we decide whether these values should be considered valid. So these are going to be very similar to what you saw for the one sample t-test, except now that we're doing a two sample t-test, you basically have to check those conditions in both groups. So one option is that the quantitative variable should have a symmetric distribution. So here we would say in both groups. We need to check and make sure that it looks pretty much like it came from a normal distribution in both groups. That's one option. Or another option is that the sample distributions should not be strongly skewed and that there should be at least 20 observations, again, in each group. So we're not so much concerned with the overall sample size anymore. We're concerned about the sample size in each group. But just as usual, the larger the sample size is, the more skew and outliers you can tolerate. So there's nothing magic about the cutoff of 20. It's just that the larger your sample size is, the more skew and outliers you can get away with. So what about this example? The sample sizes are definitely less than 20, right? We've got 10 and 11 in each group. So even though the overall sample size is 21, that on its own is not enough to do it. But looking at these dot plots, I would say they look pretty nice. They actually look nice and symmetrical. And so I would probably say that the validity conditions are met here. Even though the sample sizes are small, we have nice symmetrical sample data. And this is sort of confirmed when we look at the p-values. We got a very similar p-value whether we used a simulation or a theory-based approach.